We started off by thinking around a brute force approach to this problem where we would find all the possible combination of solutions. But it didn't take us long to realize that in this case, at first, all M courses could be allotted to any of the N professors, making the time complexity big O of N powered M. This means that if we have 40 professors in our department and 50 courses to distribute among them, it would take our code 40 power 50 iterations to give us a result. This corresponds to about 40 power 40 minutes of runtime on an average machine. Thus, we knew that this approach will not work. This is when we also realized that there is an issue with a particular caveat in the question. In the worst case of every course being in the preference list of every professor, a total of, at best, n factorial solutions are possible, which is impossible to print as the value of n gets bigger and bigger. So we removed this factor out of the question and tried to find the most optimized solution to this problem. We did a lot of research online but didn't find anything that was directly relevant on the internet. We found Kuhn's algorithm and Edmonds' algorithm, but they weren't directly applicable to our problem statement. Thus, we decided to develop and create our own algorithm to this problem, loosely inspired by Kuhn's algorithm. We will now present our algorithm. This is a dry run of one of the test cases of our program. Let us say that there are 4 courses 1, 2, 3 and 4 and 3 professors A, B and C. Let us say that the capacities of professors A and B is 1.5 each, that is they fall in the X3 category, and the capacity of professor C is 1, which means that the professor falls in the X2 category. Now let's say that professor A has preferences to courses 1, 2 and 4, professor B has preferences to courses 1, 2 and 3 and professor C has preferences to courses 1 and 3. This can be alternatively written as course 1 to be allotted to professors A or B or C, course 2 to be allotted to professor A or B, course 3 to be allotted to professor B or C, and course 4 to be allotted to professor A. Now let's start with mapping courses to our professors. We start off with course number 1 and see that it can be allotted to professors A or B or C. Since professor A has 1.5 slot remaining, we allocate the entire course of 1 to professor A. After this allocation, professor A has only 0.5 slots remaining. Now we move to course number 2. We see that course number 2 can be allocated to professors A or B. Since professor A has 0.5 slots remaining, we allocate 0.5 of course 2 to professor A and the remaining 0.5 to professor B. After this allocation, professor B has one entire slot empty. Now we move to course number 3. We see that professor B has one entire slot empty and which this can be used to fulfill course number 3. Thus we map course 3 to professor B. We encounter a problem now where course number 4 cannot be allocated to professor A, which is the only preference given by the profs. Thus, we need to rewire the mappings. We see that course number 1 can be allocated to professors A, B or C. Since we want to allocate course number 4 to professor A, we try to allocate course number 1 to some other professor. We can't allocate course number 1 to professor B since professor B's slots are fulfilled. However, professor C's slots are still empty and we can allocate course number 1 to professor C. Thus, we allocate course number 1 entirely to professor C and break the link between course number 1 and professor A. After this change, we notice that professor C has 0 slots remaining but professor A has one entire slot empty. Now we can go ahead with mapping course number 4 to professor A. This fulfills our mappings and thus our dry run is complete. We now start with the explanation of our code base given in our GitHub repository. As one opens our GitHub repository, we see that there is a main folder. Our initial approach to solving this problem was to create multiple files of different classes named course and professor. The respective .h files contain the interfaces for each of these classes and the .cpp files contain the implementations of these interfaces. These are the methods that we have used for course and these are the methods that we use for professor. After implementing these, we now go to the main.cpp file. Implement the input-output system. Here, for the input, we use the IOStream method, and for the output, as another function named writeData has been created. However, while implementing this algorithm in main.cpp, we run into a problem of integrating all the class files with main.cpp. Since this gave us compile time errors, we decided to change route and adopt the single file approach. This can be found on the main.cpp file in the GitHub repos homepage. In this file, we have directly expressed the class course and the class professor above the main function. The respective methods have also been elaborated here. After this, we now start with the main function. In the main function, we have two maps. These maps are initial map and final map. The initial map is a map of course to professor with a list of all potential connections. Wherever a potential connection is possible, the cell which indicates the connection between the course and the professor is marked with 2, denoting that there are 2 empty 0.5 valued slots remaining to be taken for that course. The final map contains the final connections or the final listings of course to professor. We now continue to understand the heart of our algorithm. In case of a course having 2 empty slots, we see that an easy connection can be made. In a case where such an easy connection can be made, the first part of our if runs and an easy connection is successfully established. On the other hand, if a course has just one empty slot, it is allocated to a professor and after a successful allocation, 0.5 slots from the professor's capacity are reduced. There is a third condition where the course might have 2 empty slots. However, none of the professors of the course is willing are ready to take it. In this case, we try to find the first professor with slots left, and if it is not possible to create a connection with the prof, we then break an existing connection with the prof and a course. We see if that course, the previous course, can be connected to another prof. Upon a successful establishment of a connection with another course, the previous link is terminated and the course that we currently have is then connected to that prof. If this is not possible, then our function returns false and the same process is then iterated over multiple profs. This cycle then continues. We now explain where we entered into problems. Upon successful completion of our code without compile time errors, we ran this code and ended up with runtime errors of segmentation fault, particularly in the highlighted section. This issue was mainly because the pointer pointing to the initial map was not the same as the pointer pointing to all profs ith element .get fdcdcpref jth element. Due to this issue, we ran into segmentation faults and hence could not successfully implement our code.